Thank you for attending our event. I'd like to welcome everyone to the seventh webinar under the East 101 webinar series. If you like our content, we hope you will help us by spreading the word and continuing to show up and support us. Thank you. So, for those of you who might not be familiar with our organization, we are advanced. We we are a specialty consulting company focused on providing advanced process engineering and flow assurance consultancy services to the oil and gas industry through the use of process simulation technology. And we were founded in the year 2003 by engineer Rafael Elias. And currently we are based in Kuala Lumpur with sales and services office around the world. Our track record includes projects which cover transient or dynamic simulation-based engineering services for design and troubleshooting, flow assurance, operational assistance, especially the OTS or operator training simulators, which are an important factor behind safe and cost-efficient operation, as well as process simulation training for steady state or dynamic simulation. Here are some of our clients. For any inquiries about our services, please contact either myself, Zihong, or my colleague, Avinash, at the numbers and email address shown. For more information is available on our website, east101.com. Through the East 101 webinar series, we hope to cover a wide variety of topics, ranging from upstream process design to downstream and refining, monitoring and surveillance, as well as analytics and AI, or machine learning. This is the webinars are scheduled to take place every other Wednesday from 4 to 5 p.m. Malaysian time. We already have our next talk lined up. The topic is Introduction to Reservoir Simulation for Non-Petroleum Engineers. And the speaker is Dr. Anwar Hamid, our engineering manager at East 101, with over 10 years of experience in the industry. Kindly mark your calendars for the 23rd of September, 4 to 5 p.m. Malaysian time. Right. So today we have Miss Madeliene as our speaker, and she'll be speaking on the topic Biochemical Reactor Modeling using Machine Learning. She's now a process engineer at East 101 and holds a bachelor's in engineering in chemical engineering from UCSI University, KL. In her final year project, she researched the use of artificial intelligence or neural networks to model biochemical processes, specifically anaerobic digestion, and has done work on optimizing biogas plant to monetize POMI into methane and fertilizer. She's previously interned with us, as well as Schlumberger. During the Q&A, after the webinar presentation, she'll be joined by Dr. Anwar Hamid, who is our engineering manager and a simulation specialist with over 10 years of experience, who holds a PhD in the computational study of enhanced oil recovery, petroleum engineering from Imperial College London. And he served an advisory role on this research, so he will help to answer any more detailed advanced questions. I guess, can you confirm if, yeah. So without further ado, Miss Madeliene, please. Thank you.
Okay. Hi, good afternoon, everyone. My name is Madeliene, and we'll be talking about the biochemical reactor modeling using machine learning. But first, I'd like to apologize for all the technical difficulties as well as the slight delay. So without further ado, let's just look at the agenda for today. First, we'll look at the background and definitions about the webinar that we'll be talking about today. So we'll look into the fundamental concepts, what is anaerobic digestion, as well as what is neural network. And then we'll look at a case study analysis, which is based off a research that I conducted in UCSI University, which was done under the supervision of Mr. Fauzi as well as Dr. Anwar. And this case study will be centered around modeling of a complex biochemical process, which is known as anaerobic digestion. So in conjunction with the case study, we'll look at the methodology as well as procedure in order to conduct the case study. Specifically, we'll look at how to model anaerobic digestion using a commercial simulator known as Aspen Plus. And we'll also look at an alternative or sort of newer approach using artificial intelligence. And then we'll look at the results and discussion from the case study in terms of how well this neural network is able to depict the anaerobic digestion process. And we will compare which computational method is sort of easier or faster and etc. Then we'll follow with a conclusion to sum up everything that we talk about, and we'll look at moving forward, how can we benefit from today's topic in other industries, especially in the oil and gas sector. So with that said, let's start off with the background and definitions for today. So two things we'll look at. One is what is anaerobic digestion. So I'll tell you three things which are how the process works and what are the parameters involved in anaerobic digestion. And finally, we'll look at why is it interesting to model anaerobic digestion using artificial intelligence. And the second thing we'll look at is deep neural network. So what is it made up of? How does it work? As well as why neural network and not just commercial simulators. So to start off, what is anaerobic digestion? So this process is basically a biological process whereby we use microorganisms to break down biodegradable materials such as our waste products. So in Malaysia, as we all know, palm oil mill effluent is one of the most famous waste that we can talk about. But aside from that, there's also like livestock waste from your crops or agricultural waste, wastewater, food waste, all these sorts of waste or organic waste can actually undergo anaerobic digestion in a digester to produce biogas as well as digestate. Now, this biogas that is produced can then be used for heating or electricity generation. You can also use biogas and upgrade it into biomethane for your car fuel or even in gas grid. And on another note, the digestate that is produced after releasing biogas, this digestate can actually be used to make fertilizer. So essentially, the anaerobic digestion process, right, is one of the most sustainable process, and it actually covers up to 9 out of 17 sustainable development goals, making it very sustainable. And there are a lot of research carried around this topic. So when we talk about anaerobic digestion, in order to get a picture of this process, right, there are three things that we probably need to look at. Firstly, what are the biochemical reactions involved in the process? And then secondly, what are the key operating parameters that we would want to take into account when modeling the process? And finally, what are the process inhibitions that may arise in anaerobic digestion? So let's look at the first thing first, which is biochemical reactions. So when we talk about the reactions, there are actually 4 stages. The first one is hydrolysis, whereby the major components such as carbohydrates, lipids, and proteins are actually broken down using a reaction with water. And they actually involve multiple reactions over here. As you can see, there are 7, 4, and 25 reactions respectively. And what happens, for instance, is, for instance, protein. It is broken down via hydrolysis into amino acid. And then from there, the carbohydrate also can actually degrade into dextrose as well as glycerol. Moving on, for the acidogenesis, there are actually 2 reactions over here. And then the third stage is the acetogenesis process. And finally, we have the methanogenesis process, which covers 2 reactions. So the methanogenesis process is where the methane is actually produced here. And so in total, there are actually 46 reactions that are involved in the biochemical reaction. And moving on, the second thing that we need to look at is the process parameters. So in terms of the parameters, the first thing that is most important in anaerobic digestion process is the temperature. So in terms of temperature, there are multiple ranges. As you can see here, there are psychrophilic, mesophilic, thermophilic, as well as hyperthermophilic. So the thermophilic is actually considered as one of the most optimum range for the reaction to take place. But depending on which stage of the process you're at, sometimes the mesophilic condition can be more suitable for the process. The second thing is the organic loading rate. So the organic loading rate basically tells you how much of biomass is fed into the reactor. And the third thing that we're going to consider is the hydraulic retention time. And this hydraulic retention time parameter is especially important because it determines how long you keep your biomass inside the digester. And finally, we look at the feed composition. So aside from the temperature, organic loading rate, as well as hydraulic retention time, the reason why feed composition is so important is because I give you an example. Your feed is basically waste, right? And waste comes from other processes. So let's just say if there is a disturbance in the upstream process or there's some sort of upset in the process, it will eventually affect your waste as well. And this waste that you take and fit into your digester would then affect your biogas quality. That's just one example. Another example that I can give you is, for instance, animal waste. So let's take cow manure for as an example. There are different types of cow, and believe it or not, different cows produce different types of manure, and this actually varies the composition as well. So more often than not, the feed composition does affect your overall anaerobic digestion process as well. So with that, we cover the second thing, which is our process parameters. And the third thing we want to look at is the process inhibitions. So in terms of inhibition, pH, for example, would be a very crucial parameter because we're dealing with biochemical reaction, like living things. So you can imagine as a human, you probably don't want to live in an acidic environment. Same thing for microorganisms, they live in a preferred pH range. And so another situation that would inhibit the process is an accumulation of free ammonia as well as long chain fatty acids. So these are some of the conditions that could inhibit the process. So now that we've looked at all three of these things, I guess by now you pretty much have a good idea of how many parameters are involved in anaerobic digestion, as well as what makes it so complex, as well as you would expect a very non-linear behavior as there are so many parameters to control and sometimes you don't even have data for them. Okay, so with that said, anaerobic digesters tend to show a stochastic response. What do I mean by stochastic response? So stochastic is basically a description of how your response is very random. You're not able to predict it precisely, and that is what we more often than not see in anaerobic digestion process due to its high complexity and non-linearity. Okay, so with that in mind, it's so stochastic. How can we then model anaerobic digestion? It's an important process, as I mentioned in the beginning, only because it's a driver in the bioeconomy sector. So in the past, there have been multiple methods to model anaerobic digestion. The first one being using mechanistic model. So mechanistic models are basically based on first principle concepts as well as scientific knowledge. And here are just some of the examples of models that have been built over the past 60 years or so. But a newer approach that we have right now to model anaerobic digestion is actually using neural network. It is a sub-branch of artificial intelligence, and it's one of the newer methods to actually model anaerobic digestion. So now that I mentioned neural network, let's just roughly go through what is neural network. So a neural network is basically some algorithms that will help you to recognize the underlying relationship between your input data as well as your output data. So with that in mind, neural network can be used for multiple applications. First thing first is classification application. So this is one of the more common examples that is used, which is classifying iris based on their characteristics. So you can see here when you input the length, information on the width as well, then the neural network is able to tell you which type of iris flower is this. So that's one of the examples. Another way you can use neural network is for prediction. So if you look at this diagram, basically what you put inside is maybe you tell whether it's raining or whether it's payday, what's the temperature like, what day of the week is it, and then the model will be able to predict for you how many sandwiches will be sold. So a similar concept can be applied even in your stock market prediction, for example, and also in regression problems. So what happens is you feed a bunch of data into the neural network and the model will try to fit into your data. So that's a regression problem as an example. And the third most common purpose of using neural network is for clustering. So these three are basically all the common ways of using neural network. And in today's webinar, we'll be focusing mainly on using neural network for prediction as well as regression problem. So now, why neural network? As I mentioned earlier, you can basically use your commercial simulator like Aspen Plus or even SuperPro to model anaerobic digestion. But I'm quite sure, like if you're in chemical engineering, you would know that if you want to sit down and actually build a simulation model, you have to input a lot of parameters and it will take time considering how complex your model is. And what we call this is basically priori knowledge. You need to have the knowledge of how the thing actually works and what are the scientific background of the process before you can simulate it in your simulator. So with that said, what neural network does is it eliminates any need of priori knowledge and introduce a black box model. So what's a black box model? Basically, you don't know what happens in the black box model. It's just a box. You feed some sort of input to it and it will be able to spit out an output to you. If I tell you this is just a general idea, but behind this black box is actually a bunch of mathematical calculations. But at the end of the day, it just simplifies by eliminating the priori knowledge. So now let's look at the basic structure of a neural network. So when we talk about neural network, this is probably what it looks like, a very simple structure. So you have your input layer, and then you have a hidden layer in the middle, and an output layer. So you feed your input here, and then at the hidden layer, some sort of computation will happen, and then it will predict an output for you. So this is what it looks like, but on a deeper level, each node actually has its own meaning. And just to give you an idea, the A here actually represents something called an activation function, which we will touch on later on. So now that we know what the basic structure looks like, and this is just a simple neural network, there is also something called a deep neural network. And this is what it looks like. So on the left, we have a simple neural network where there's only one hidden layer, whereas on the right, we have a deep learning neural network where there are multiple hidden layers. And for it to consider as a deep learning neural network, you have to have more than 3 layers or so. And the thing about having a deep learning neural network is that your structure is more complex. So you're able to model more non-linear processes with the problem of having more parameters to tune, which also translates into requiring higher computational power. So there are also drawbacks as well, but with the current advancement in terms of the computational power, it is actually possible to use deep learning neural network. So with these differences in mind, let's jump into the just one node in the neural network. So as I mentioned earlier, there are multiple layers, and in each layer, there are multiple nodes. So now we're just looking at one node. So in one node, there are actually multiple parameters that you can look at. For instance, your biases, the synaptic weights, as well as the activation function. So how are we going to relate our input to our output? The method here is actually to tune your bias value as well as your synaptic value. So these are the two values that you will need to tune in order to relate your input to the output. But this is just one node. In a deep neural network, you can have up to hundreds of layers, and you can have up to thousands of neurons, basically thousands of this circle thing, where there are a lot of weights and biases. So how then can we optimize these biases and synaptic weights? The method to do this basically is to use an optimization algorithm. So conventionally, people use something called the gradient descent or backpropagation algorithm. And here's just an image to show you how it basically works. So what happens in the gradient descent algorithm is that some sort of input will be fed into the system, propagated through the system, and then in the hidden layer, a computation will happen and the output will spit out a predicted value. So this predicted value will then be matched against a targeted value, and the error which is calculated will then be propagated back through the network in order to update the synaptic weights. So you can see here, this curve basically acts like an objective function. So our objective function in a regression problem is more often than not for instance, something like mean square error, or even root mean square error, or mean absolute error. So it's the loss. And your objective ultimately is to minimize this loss. The smaller your loss, that means the nearer your predicted value is to the targeted value. So what happens here is once you calculate the gradient, it will be propagated back through your neural network in order to move your weight to an optimal value. So that's basically the idea of gradient descent. And when we talk about gradient descent algorithms, there are multiple algorithms as well. Not to overwhelm you, but just to give you an idea. So you can actually identify that there are some algorithms based on batch size. So for instance, a batch gradient descent. Just to explain to you, if let's just say you have 100 samples of data, what happens in a batch gradient descent algorithm is I will feed this 100 samples of data through my neural network, and then my network will predict a y value, and this y value will then be compared to a targeted y value, and the error will be propagated back through the network. Okay, and this will be done in a single iteration. And then the second type is called a stochastic gradient descent, whereby if I have 100 samples, I will feed one sample through the network, predict the value, compare to the targeted value, get an error, and then update the synaptic weights and proceed with the rest of the 99 samples for one iteration. So it's different than the first one. And then the third type is using a mini batch gradient descent, whereby the 100 samples are split up into smaller batches, fed into the neural network, predict, calculate the error, and send back through the synaptic weights as well. So this is another type of optimization algorithm. This is just for your information. And there can be more variations to it as well, like including a momentum parameter or a Nesterov accelerated gradient parameter. So this just shows you that there are many algorithms available out there, and some even includes this thing called adaptive learning rate. So learning rate basically controls how quickly your model is able to adapt to the problem. And to give you a quick idea, is that if your learning rate is too small, then your model will take its sweet time in order to reach until the global minimum, or may not even reach there. If you have a good learning rate, then your model is able to reach to the global minimum in a short amount of time. But if your learning rate is too high, you will find that your model is not even able to reach the global minimum point. So with that said, here are just some of the examples of an adaptive learning rate optimization algorithm. And that's all for the backpropagation algorithm. Now let's look at a different type of algorithm called meta-heuristic optimization algorithm. So a meta-heuristic optimization algorithm is sort of like a higher level approach whereby they use some sort of heuristic in order to find a sufficiently good solution to an optimization problem. So here are some of the examples of meta-heuristic algorithm. Firstly, we have evolutionary algorithms. We have physics-based algorithms, swarm-based algorithms, bio-inspired algorithms, as well as nature-inspired algorithms. Now, just to give you an idea of what I mean by heuristics, so let's take genetic algorithm for an example. So genetic algorithm basically works like this. Imagine in the reproductive system, right? Normally, the fittest individual will naturally be selected in order to undergo reproduction. So similar thing will be applied in optimization. The particle which is able to reach an optimal value will tend to attract the rest of the particles towards it. And to give you another example that may be more relatable is like firefly algorithm. So as we all know, firefly basically shines quite bright in the dark. And so how it works here is, let's just say you have two fireflies in a situation. And if one firefly is nearer to the good solution, it will shine very bright and attract the other firefly to its location. And what happens then when you compare this to an optimization situation is that if a firefly is very near to the optimal solution, what happens is it will draw the other fireflies to that solution in order to find the most optimal answer. So these are just some of the examples of a meta-heuristic optimization algorithm. Now, in this research, we actually use particle swarm optimization as the primary focus. And so what is particle swarm optimization? This optimization algorithm is actually based off the social behavior of birds flocking. And so if you can see from this 3D diagram, what happens is the particle starts off from a randomized location. And then based on this randomized location, the fitness or basically the error, you can say the error, is calculated in order to determine how near this particle is to the optimal location. And then based on this information that we have, it will update the values in the algorithm in order to sort of drag all the other particles to the optimal location. And at the end of the day, we will determine whether the optimization algorithm is converging to an optimal solution. If yes, then basically we reach to an answer, to an optimized answer. But if no, basically we have to repeat the whole process and evaluate the loss and score function as well, then go through the whole updating process until we're able to converge to a minimum point in the objective function. So with that in mind, there are also variations to the particle swarm optimization algorithm. The first one is called the global best algorithm, whereby when updating the particle, it would consider the whole population of swarm of particles. Whereas the other version is the local best optimization algorithm, whereby in updating the particles, it will only consider a certain number of neighboring particles. So for example, if I have a population of 20 particles, maybe I might only consider the 5 neighboring particles to me before I decide which particle is in the best location. So that is the difference between local best PSO as well as global best particle swarm optimization. So with that in mind, let's just look at one of the example of how a particle swarm optimization algorithm can be written in Python. So what you're looking at right here is a Jupyter notebook. And so first thing first, you would need to import all the packages that you require. Subsequently, what you want to do is you would want to read your data from, depending on what your source is, read your data into your code. And then, as I mentioned earlier, the activation function, which introduces a non-linearity into your neural network, you would have to write a custom activation function for it. Subsequently, after you have that, you can develop your PSO code in Jupyter or in any other IDE that you prefer to use. And from there, once you have your particle swarm optimization code, you would then have to decide, do you want to use a local best particle swarm optimization algorithm or a global best PSO algorithm? So in this case, let's just look at an example of using a local best PSO algorithm. Once you've defined all the parameters required, you can basically run the test, and the results that they spit out to you, the best position, basically consists of the value of all the synaptic weights as well as biases of your neural network. And so with that said, this is how it works for the local best particle swarm optimization. With the best position available, now you can proceed to do a prediction. And once you actually have your prediction functions well written out, incorporating the optimal value of your position, you can then proceed to do to run a prediction which will generate the following results. So from this graph, you can see that the blue line is your targeted result, and the PSO algorithm is able to predict the red color results, which is very near to what you want. And the R-square value, 0.967, just shows how well your model is able to fit to your targeted results. So this is just an example of how you would run a particle swarm optimization algorithm. And so with that said, since we have already covered all the major concepts required, now we will look at a case study analysis with all the concepts that we have so far. So coming back to the story of anaerobic digestion, in the current situation, what we have is a biochemical reaction, which is very complex due to a lot of parameters as well as reactions. And so the challenge here is, how are we going to model such a complex reaction? And how are we going to maximize yield when there are so many parameters to take into account? How are we going to develop an optimization strategy when the temperature could be in any range, the pH could be in any range, and even your feed composition would vary as well? And so with that said, the ultimate thing that we're trying to do here is to develop a fast and efficient model in order to depict anaerobic digestion. So in order to do that, we would use something called the deep neural network, which we covered earlier. And we would target to predict the biogas yield, for example, in this case study. And how are you going to do that is you can either supply real plant data to the neural network, or you can supply simulation data to the neural network. For the purpose of this case study, we will focus on using simulation data in order to train our neural network to predict biogas yield. So we'll just look at an overview of the procedure we'll be using, and it will be basically separated into 3 main parts. So for the first part, in step 1, we would build a steady-state simulation model in Aspen Plus, and then proceed to convert it to dynamic simulation model. And in the last stage of the first part would be to collect the simulation data for our neural network. Then in step 4, we can then construct the deep learning neural network, and finally compare the learning performances of different types of optimization algorithm. So let's look at the first step first. So for steady-state simulation model, as I mentioned earlier, these are some of the past examples of simulation models available. And the ADM1 model is actually one of the most complex model out there, and it's able to depict the anaerobic digestion process almost very well. And there are also several attempts in order to simplify this model. One such model is actually by Rajendran, which we'll be using in this particular case study. So it's called the novel process simulation model in Aspen Plus. And this particular model is actually able to cover all 46 biochemical reactions in anaerobic digestion. It also covers the key operating conditions and also covers the process inhibition. So ultimately, it is, although simplified, it is still able to model anaerobic digestion and give us the simulation data we require for our neural network. So this is what the simulation model would look like, a steady-state simulation model in Aspen Plus. So the first thing we have here is a stoichiometric reactor to model the 13 fractional conversion reactions representing the hydrolysis reaction in stage 1 of anaerobic digestion. The second reactor that we have is a continuous third tank reactor, which consists of 33 kinetic reactions to model the remaining biochemical reaction in anaerobic digestion. And what we have here is calculator blocks in order to calculate the kinetic constant, which is required in the RCSTR, the continuous third tank reactor. And for this simulation model, the feed itself, the composition will be based off a literature, so as well as the operating condition and benchmark result to validate our model. And so this is basically the validation that was already done for the steady-state simulation model, and it's able to actually depict the anaerobic digestion process with up to 3.7% difference, which is fairly acceptable. So that's the first stage. And then secondly, what we'll do is we'll convert the model to a dynamic simulation model, as you can see here. And so, as I mentioned earlier, there are multiple operating parameters that we need to take into account. So there are temperature, organic loading rate, hydraulic retention time, as well as feed composition variation. However, for the sake of this case study, we would fix the first 3 parameters, temperature, OLR, as well as HRT, and we will only consider the feed composition variation. And so how are we going to achieve that is by using a noise generation block based on the Gaussian noise model. So the biomass is basically already split up into 5 of the major constituents, which are protein, lipid, carbohydrate, inert, as well as water. And then subsequently, a noise block is subjected to the input. And when you want to define a noise block in Aspen Plus, the 2 information that you'll probably need is the datum, which is the reference point, as well as a standard deviation, which is how much does the noise signal deviate. So these values are actually based off from literatures. And in terms of the output, we also subject some sort of noise to the biogas outlet to model flow inaccuracy. So with that in mind, just to give you an idea of what are some of the assumptions that were made for this simulation model, well, firstly, the model was assumed to operate continuously. And then secondly, in terms of collecting the data later on, we would assume that the model initializes at steady state on day 0. And thirdly, the pre-exponential factor that was calculated by the calculator block would remain constant in the Aspen Dynamics model. And then in terms of the lag time, we consider it to be negligible because the reactor volume is so small, so we would assume that the response or the lag time is considered negligible. So the 5th assumption would be that the noise block that we use, which is Gaussian noise model, would be valid because Gaussian noise model is one of the model which is most commonly used to model random noises in processes. And the final assumption that was made is that the decay ratio we will consider is 5%. So finally, the last step into achieving the simulation data collection is to do a pulse test and then do the data collection. So the purpose of the pulse test is just to test your simulation model and see how would it respond to a disturbance. So in this case, a sharp peak was induced, and it was found that it took about 1 to 2 days for our biogas to stabilize in terms of the output. And one thing to note is that because the dynamic simulation model that we constructed here was not used to do any transient behavior studies, so in this case, we just proceeded to take data daily. However, in the future, there are actually further improvements possible to the simulation model in order to study any transient behavior. So with that in mind, the daily data was collected for biogas. And just to give you an idea, if let's just say there is no feed composition variation where everything is perfect and ideal, you would have, this is what your input will look like, and your biogas production will look something like this. However, when we incorporate feed composition variation into the simulation model, you would find that this is the input into the model, and your output biogas production would have a more stochastic behavior. So this basically depicts the fact that in our case, when we use cow manure doesn't have one composition throughout. They are varying compositions. So this depicts that. So now let's take a closer look to our data set. So our data set basically consists of this, whereby the maximum value is 6.4, the minimum value is about 1.8 liter per day, and the mean value is 4.0673, and we're looking at a standard deviation of 1.3473. So this is the data set that we are dealing with. So in the subsequent stage, we would want to look at how do we build a neural network from here, right? So as I mentioned earlier, we are not looking into the transient behavior in terms of building the neural network. And since the lag time, we would assume for it to be negligible. So subsequently, what we do is we would treat the data as 100 discrete samples of data in order to train our neural network and etc. So first thing first, these 100 samples will be split into 80% for training the model. That means we'll feed this into the neural network, and the network will be able to learn what is the relationship between our input as well as output. And then subsequently, 10% of the data is used for validating our model. When I say validation, this is just to give you an idea of how it works. So sometimes when you feed data into your model might underfeed the data. That means like the relationship, it does not cover the whole point. Or it may overfeed your data in the sense where it fits too perfectly to your data, so much so that if I were to introduce a new data here, it might not be able to predict well. So ultimately, what we want is a good fit of the model. And by using a validation set, we will actually be able to test that situation. And then finally, 10% of the remaining data will be used for testing the model in order to see what is the generalization ability. So this testing data will be something that is not seen by the model previously during training. From that, we can tell how well our model can perform in terms of predicting new data. So with all of this in mind, since now we already have our simulation data, let's just take a look at how do we construct a deep neural network from there. So when you want to construct a deep neural network, one of the main things you need to decide first thing first is what is your input going to be. So in this case, since we're looking at the variation of feed composition, so naturally our feed would be the mass composition of carbohydrate, proteins, lipids, innards, and water. And the sixth feature that we're using here is the biomass volume flow rate to identify what is the quantity that is fed into the reactor. So now that you have your input, you also need to know what do you want to predict. And in our case study, we want to predict the biogas volumetric flow rate. So this would be just a single output. And with this information in mind, aside from deciding your input and output, you also need to decide what is the structure going to look like. So these things would be called hyperparameters, whereby in a neural network, especially a deep learning model, you would have multiple parameters that you will need to tune in order to find the best configuration or the most optimal configuration. So for instance, in the deep neural network model, you would have things like the number of hidden layers, which you'll need to tune. You would also have something called the number of neurons in each layer, as well as the activation functions that you will need to tune. So these are just some of the hyperparameters that needs to be tuned in a DNN model. So aside from that, in order to actually tune your model, you also need to have optimization algorithm, as we spoke about previously, the backpropagation algorithm. So these things can be tuned as well, and they are considered as a hyperparameter. So like the optimization algorithms that we spoke about earlier, like ADAM, SGD, etc. The learning rate, which is how fast your model is able to adapt to the problem. We also have momentum, batch size, as well as number of iterations. So here are some of the things that you need to look at for backpropagation. Whereas for the meta-heuristic particle swarm optimization algorithm, you probably need to look at which optimization algorithm is the best. Do you want to choose global best or local best? And then in terms of the parameters that are used in the algorithms, so for example, the inertial weight, this is something we can tune as well. The cognitive parameters, as well as the social parameters. So these three parameters are actually part of the equation, and it will affect how fast your particle swarm optimization algorithm is able to solve the optimization problem. So aside from these four things, there are other two things that you can look at. One is swarm size, as well as number of iterations. So basically, this all constitutes the hyperparameter, and there are things which you can adjust in order to derive at an optimized configuration. So with that said, how do we then tune the hyperparameters? So one way you can do that is to use a trial and error method. So you basically set one optimization algorithm, run your model, see how the result is like, and then repeat for, I don't know, 100 times or 1,000 times, that's possible, using trial and error. But of course, there is a smarter way to do it as well, which is to use some sort of a search algorithm in order to test out multiple trials at one shot. So there are two ways to do it. One is called the grid search, whereby you test out every possible combination in the configuration. Another way to do it, which is sort of faster, it's called the random search, whereby it will pick out certain combinations to test out in order to derive at an optimal solution. So now let's look at another demo. So the hyperparameter tuning can actually be done in Python itself as well. And so what you will need to do is to import some packages into the notebook. And then normally what I would like to do is to it's something called seeding, whereby you would kind of standardize the randomization, which makes your result reproducible. And another thing you will need to input is your model itself. Like, what is the model you're trying to tune here? So our objective here is to basically tune the number of layers. So as I mentioned earlier, when you're trying to tune the layers, you also need to find like how many neurons do you want to have, what are the activation functions that you want to have in each layer. So this is what we're trying to do here. So with the model available already, you would also need to process your data that you're going to fit into the model, split it into the training, validating, and testing data sets that we mentioned earlier. So once you have done that, then yep, so these are like the codes where you would process your data and split the data accordingly. So once you've done that, then you also need to come up with the functions to train your model, validate your model, as well as test your model. So these are all the functions for that purposes. And then comes the debugging part. So before I do any hyperparameter tuning, personally, I will always do some sort of debugging to make sure that the codes in the beginning are all functioning well before I jump into any sort of tuning of my hyperparameters. So once that is done, you can see here basically that we have results for our determination coefficient, our objective function. They all have a result, so we know that the code is working fine, like we get a result. Then we can move on to hyperparameter tuning. So from the beginning, you have your model. Right now, what you're doing here is you're wrapping the model around some sort of a loop whereby it will perform the search for you instead of you basically doing a trial and error and running the model multiple times. So by constructing this function, you will be able to do a tuning subsequently. Okay, so this function over here, once you run it, it will basically generate a list of the number of trials that you're trying to solve. So basically that's how it works. So at the end of the day, this is how you tune your model, whereby you can have multiple trials at the end, and based on the result of your loss and score matrix, then you can determine basically which combination of the configuration works best or most optimal. So moving on, now that you have an idea of how hyperparameter tuning works, in the case of this case study, the stage one of hyperparameter tuning that we'll be doing is how to tune the model topology. That means the number of layers, number of neurons in each layer, as well as the activation function. And then in the stage two, we would tune the conventional backpropagation algorithm, whereby we will look at the optimizer hyperparameters as well as the training parameters that we mentioned earlier. And this all can be done in a library in Python called PyTorch. And subsequently, the second type of optimization algorithm that we spoke about earlier, which is meta-heuristic particle swarm optimization. So you can tune the hyperparameters 1 as well as hyperparameters 2, which consists of the things we spoke about earlier, which is the PSO algorithm, whether it's global best or local best. And then we also spoke about the inertial weight, cognitive and social coefficients, and the swarm size and number of iterations. So this 5-stage hyperparameter tuning pipeline would basically cover all these things in order to derive at the most optimal solution. So the particle swarm optimization was actually constructed in PySwarms, which is the package, it's just a library in Python. But of course, you can also actually just write out the code yourself because the algorithm is fairly simple to write out. So now that we've covered the hyperparameter tuning stage, let me just show you some of the results from the hyperparameter tuning. So earlier, as I mentioned, in stage one, we tuned the topology or how the model looks like, right, for our neural network. And this is the results that was obtained for this case study. So the optimal configuration essentially would be like a 3 hidden layer model with soft sign, leaky ReLU, as well as sigmoid activation functions for the model. And so with that said, once you have that optimal DNN model structure, so 2 things you can do. First one is we would try out the backpropagation algorithm. So as we spoke about earlier, there are multiple like optimizers for backpropagation from ADA delta all the way up to SGD with Nesterov accelerated gradient. So what you want to do here is you would want to identify what is the optimal setting for each of the parameters from learning rate all the way up to your weight decay or learning rate decay and momentum. So in stage 2, we identified what are the optimal values already. So these values will then be put into stage 3 and then optimize the batch size as well as the number of iterations, or we call it max epochs. So from this graph, you can see here that basically it shows you what is the mean square error loss, which is your objective function, against the number of iterations. So for different optimizers, it takes a different amount of iteration in order to reach a lower loss. And as you can see, certain optimizer algorithms actually reach a lower loss as compared to others. And in the case of this, let me show you some values to get a better idea. So as you can see here, the ADA-max backpropagation algorithm actually managed to reach a lower RMSE value, which is root mean square error loss, as well as a mean absolute error loss. And in terms of the determination coefficient value, it got 0.9705, which is the highest as compared to the rest. And as I mentioned earlier, the R-square value is able to tell you how well does your model fit to the targeted data. So now that we have that, and we know that ADA-max is the best performing backpropagation algorithm in this case, let's look at the second thing, which is to optimize the particle swarm optimization algorithm. So similarly, the DNN structure that you have earlier will now be optimized with PSO algorithms. And so we try out both the global best algorithm as well as local best algorithm. And what we're tuning here is the C1, C2, W, and K value. So after tuning this value, it was shown that the local best algorithm actually performs better. And so with this value of C1, C2, W, and K, we input it into stage 5 and then tune the swarm size as well as number of iterations. So this example is the example for global best particle swarm optimization. And there are multiple number of iterations that was tested out. Okay, and at the same time, we also try out for different number of particles or swarm size for the particle swarm optimization algorithm. And as you can conclude from this graph, is that as your number of particles increase, the computational time required also increase because you have a higher number of parameters to tune. At the same time, for the number of iterations, when you have higher number of iteration, which is indicated by the blue line, as compared to, let's just say 50 iterations in the orange line, you would naturally spend more time in terms of computational time for a higher number of iterations. So this is just an idea of how it works. And based on the results from stage 5, we would find that the local best algorithm actually performed better than the global best algorithm. So what we would do here then is to take this local best algorithm and then compare it to the AdaMax backpropagation algorithm that we got from our conventional algorithm. That's a lot of algorithms right there. Now let's look at the performance comparison. So to summarize, from the backpropagation algorithm, AdaMax was the best performing one, whereas from the meta-heuristic particle swarm optimization, the local best PSO was best performing with all the optimal settings that we've put inside, okay? So with that in mind, you would find that although the loss and score matrix of AdaMax is slightly better than RMSE, so the lower your loss, the better your function, because that means that your targeted value is close to your predicted value. And so even though AdaMax performed better in that aspect, in terms of computational time, the local best particle swarm optimization actually performed much better with only 2.43 seconds as compared to 51 seconds in AdaMax. That's about 21 times faster. So that actually shows that there's a lot of potential in terms of cutting down on your computational time. And here are the predictive capabilities of both models. As you can see here, that the targeted value and the predicted value actually lies very closely to each other. This is just the training stage, but if you want to know about the generalization ability, you would naturally look at the testing stage to see how well it fits. So with that in mind, let's just look also at the goodness of fit, which is determined based on your R-square value. So it would show you how well, so these are basically just the testing data, and it will show you how well it lies in accordance to your model. So you have your predicted values as well as your targeted value. Then finally, in terms of convergence, so convergence is basically a graph of your mean square error loss, which is the objective function, to the number of iterations. So from here, you will be able to see that in the beginning, the local best particle swarm optimization actually decreased very fast to a very low loss in a very short number of iterations. However, as time progressed, the AdaMax backpropagation algorithm actually sort of overtakes the LBEST PSO and reach a lower mean square error loss. But somehow it requires a little bit more number of iterations. So in terms of convergence, however, they both managed to reach a fairly small mean square error loss. So that would basically sum up the comparison in terms of the optimization algorithms that are available. So to conclude on what we've actually done or spoke about today in the whole webinar, first thing first, we actually look at comparing a mechanistic model to DNN model. So mechanistic model was basically the construction of the Aspen Plus model, whereby a lot of inputs were required. You need to define multiple reactions, and then in order to derive at your simulation data. Another thing we looked at was the DNN model, which was fairly simple. All you had to do was just supply some data to your model, train your model, and you are able to predict some sort of output. And what you can tell from here is basically, aside from the coding, the DNN model is a lot simpler in terms of processing your data and making predictions, and it definitely eliminates any need of priori knowledge, which could be very useful in complex processes such as anaerobic digestion, where there are multiple parameters to look into. In terms of accuracy as well, the DNN model was able to predict with reasonable accuracy overall, making it a very viable alternative approach. And then in terms of the algorithms that are available, we looked into the conventional optimization algorithm, which is backpropagation. We also look into a newer approach based on meta-heuristic algorithms. So as you could tell earlier from the final results, the meta-heuristic algorithm actually have potential of cutting short the computational time up to 21 times faster. Of course, this is only on the scale of the case study that we have performed. However, it does still raise that potential of applying it on a larger scale when you're comparing it in terms of computational time. So finally, although our whole webinar was based on anaerobic digestion, you could actually apply a similar concept into other modeling applications as well. And to just give you an example, if we're talking about the oil and gas industry, for example, looking at the petroleum sector, for instance, upstream, it is actually one of the industries with a large amount of data available. And to be honest, you can apply this even in exploration and reservoir engineering. Wherever there's data possible, you can use neural network in order to predict something based on your input data. So another thing that you can also do with neural network, also looking at the oil and gas industry, perhaps more towards the downstream side, is you can incorporate neural network predictions into modeling and control systems of, for instance, distillation columns. You can also use it to predict stuff like your bubble point pressures of crude oil, and there's so much more potential of using neural network as a whole. So there's an endless possibility to that, not just in anaerobic digestion. So with that, I would just like to conclude today's presentation and thank you so much for your time. So I will pass the floor back to Zihong.
Thank you, Madeleine, and thank you for an educational and very inspiring session, if I say so myself. Yeah, as Madeleine has said, this technology, which we can apply in oil and gas, either upstream or downstream, is something that has great potential. If I could have control, I can move through the closing slides. Yep. So now this marks the beginning of the Q&A session. If anybody has any questions, please write it in the chat box, and we'll read it out for the benefit of all the attendees, and we'll address your questions. Ms. Madeleine and Dr. Anwar will be here to address your questions. Thank you. So Encik Fauzi's question is, why limit hidden layer to 3? Madeleine?
Okay. Hi, Mr. Fauzi. To answer your question, why limit hidden layer to 3? So in the specific case study, we actually tested out 3 hidden layers, 4 hidden layers, as well as 5 hidden layers. And we, as I mentioned earlier, there was a tuning process. So based on the optimization process, we found that the 3 hidden layer actually managed to achieve a lower loss as well as better performance overall. However, if you want to test out even 10 hidden layers, it's actually okay. It's just that you will consume your computational time, and sometimes it's not even worth it because you don't get as good a result as you would with a smaller amount of hidden layers. Yeah, that's what I would say. Anwar, would you like to add on?
No, I think you've covered pretty much everything.
Great. Thank you, Madeleine. I have a question actually. With regards to the number of hidden layers, is there some kind of heuristic, or does the number of hidden layers represent some physical driving force that can be imagined in some way?
Okay. To answer that question, based on the research process that I did, right? In terms of number of layers, there wasn't actually any heuristics to define that. However, if you're talking about number of neurons, more often than not, we actually start off with some sort of heuristics. For instance, the number of neurons is probably between the number of input that you have, or there will be a heuristic. So it could be, for instance, the number of input plus the number of output divided by 2. That could be a starting point, etc. So there would be a heuristic to guide the number of neurons. Whereas if talking about number of layers, to my knowledge, there's actually no heuristic to drive that. So that's where the hyperparameter tuning pipeline would come in handy, because then you could test out multiple layers and get an optimal result without any heuristic. Yeah.
That's great. Thank you very much.
Okay.
So about extrapolation problem, how do you overcome this? I'm not sure if that makes sense, Madeleine.
Okay, so in the case study that we conducted, we did not deal with any extrapolation problem. Anwar, would you be able to answer this question?
Yeah, pretty much everything. Whenever we deal with regression, I think this extrapolation problem keeps on haunting. So if you're not familiar, like if you still remember from Madeleine's presentation, when we feed the data to perform the regressions, we sort of have a range of data from minimum to maximum. And then whenever we want to predict something, the model usually only works between those boundary. So if you want to go outside of this specified boundary, this is when you start dealing with extrapolations. So in general, this is nothing that we can do because it's just outside from what available data that we have. But for engineering, it's a bit different because sometimes you might be able to sort of bound your problems and uh, have your solutions to at least have some minimum or maximum in terms of your predictions. So to recap, in general, there's no solutions to handling problems associated with using the model for extrapolation purposes, but specific to engineering, in many instances, we might be able to sort of hard limit the solutions or the predictions such that we know physically what will happen to the system. Yeah, I think that's my answer. Madeleine, do you?
Mm, I think that
Yeah.
about covers all of them.
Unfortunately, Medley didn't get this problem during
Yeah.
his last
So
presentation at
yeah.
university.
Right. Thank you, Mr. Fauzi.
I
Okay.
think I have a questions for Madeline. How easy was it or how hard was it for you to pick up all these things?
Um, I think it's actually fairly accessible because there are a lot of resources online to learn, as well as a lot of models, already built models online that you can actually refer to in terms of constructing your model. So for me, I was able to at least get a grasp of this whole thing within 4 months. As I mentioned earlier, this case study was actually based off a research project for about 8 months. So yeah, actually, it's very accessible in my opinion in order to pick up Python programming from scratch and then learning neural network due to the amount of resources available online. Yeah.
Okay. I guess if there's no more questions, thank you all again for your time in attending this webinar, and we will end it here then, and we'll see you next time.